Hello, my name is David Lee Jr. This is Lab 4, focusing on oscillations. Just a little table of contents. We're going to start with the introduction to the experiment, then we're going to analyze some motion, build a computational model, and then answer what does it mean. So some key concepts, as always, is going to be Newton's second law with both the position update formula and the velocity update formula as shown. In addition, we're also going to be discussing some forces due to gravity, spring, and net force, and also be discussing energy principle and work, particularly kinetic energy, gravitational potential energy, and spring potential energy. Some formulas we'll be using are shown. We're going to need formulas to calculate the weight force, which is Fg, 0 in the x position, negative mg at the y position, and 0 in the z position. Spring force, which uses the spring constants and the relaxed length of the string and the L hat vector. Kinetic energy, which is going to help determine the energy pertaining to motion. Gravitational potential energy, which helps us measure the potential of the gravity energy. And spring potential energy, which is also somewhat similar to the spring force. And also a very key concept is the application of the energy principle, where delta E is equal to work when it's the total sum of all the forces or all the energy on a system. And we're going to be selecting the ball, and the spring and the ball for our system when we're calculating the force, and then for the potential energies and the energy principle, we're going to be using the spring, the ball, and the earth. I'm going to have to, excuse this, I'll have to go find that video because it isn't uploading. So this is a screen recording of the motion and tracker. So you can see here, I'm marking the position in the center of the mass, and we're getting both X and Y data because it's moving in both the X and Y direction the entire time. And also the object started from rest. So to build a computational model, we had to put in some initial conditions, including the gravitational force constant, the spring constant, the relaxed length of the spring, as well as editing the 3 lines to include the length of the spring, L hat and S, while also accounting for the system's energies, for the kinetic energy, the gravitational potential energy, the spring potential energy, and the total energy. Also accounting for the ball's mass and the ball's initial position, which I found in tracker. And because it started from rest, the velocity is at 0. Some edits to the starter code I made was to define the initial energies while we're iterating through the code. Make sure we calculate F grab according to the formulas that we looked at a little bit earlier. Same thing for F spring, and then summing those 2 forces of spring and grab to find F net. Then using Newton's second law to update and change the ball's velocity and position, while also making sure we account for updating the spring and the spring's current length and all the things pertaining to the spring. In addition, we also have to calculate the energy changes for every iteration. As you can see before, as you can see on the screen, where delta K is going to be equal to the energy subtracted from the initial energy. Again, I won't be able to show it. I'm going to have to just go over here real quick, show the computational model. Here, choose the file, load in the data from tracker. Dang, it's going to be a lot of fun. Yep, and then you can see the spring oscillating and showing the change in energy versus time and position. Yeah. So, looking at the results, the change in energy, the spring force and the gravity force are equal and opposite every time they iterate and they oscillate. And the kinetic energy is changing twice as fast as the gravity and the spring force, while the total energy remains constant. The observed versus predicted, it does seem that the observed motion is a little bit higher in the Y position, but pretty close in the X position, and this probably has to do with human error and tracking, as well as the way that we calculated the spring constant, because we used, and because we are accounted for both Y and X motion. I only used the X position when we calculated it, so it may not have accounted for as well as it would have for the Y position. And to answer what does it mean, is the energy principle satisfied? So the energy principle says that delta E is equal to work, which is the sum of all the total energies in the system. And because the sum of the total energy is 0, and we know that no work is being done because the spring and gravity energies are canceling each other out, then the energy principle is satisfied. What does it mean, part 2? As I was saying before, we're estimating oscillation for only X when we created this model, but there's oscillation for both X and Y over a different time period and over different spans of oscillation, right? So for X, it took 4.748 seconds to oscillate 3 times. So T, the time of oscillation, is 1.5826. And for Y, it took 5.128 seconds to oscillate 3 times. So T is equal to 1.7093. Obviously, these are not equal. There's a pretty sizable difference, which explains the discrepancies between the observed and the predicted when it came to plotting the Y changes over time. And this is because the spring constant K can be found by rewriting the equation for time of oscillation. Thank you for watching.